Now we're finally ready to go on to the calculating LHA. Remember, this is technically something we could have done right away after we found GHA. It's just usually easier to get the declination and the assumed latitude before we move on. If anything, just because this stuff requires working in the book and what we're about to do does not. So you could just use all your book, then finish that up, put it to the side, and now we can move on to calculating GHA. Now, the first thing we need before we calculate GHA is we need to calculate our assumed longitude. So I'll write that here as assumed longitude. But we can't even necessarily just right away find what our assumed longitude is. There needs to be a couple steps taken beforehand. Now remember, LHA ultimately is equivalent to the difference of longitude between your position and the sun, whereas GHA is the longitude of the sun, so the difference of longitude between Greenwich and the sun. Now, if you want to actually work out what those are graphically, we could make one of the diagrams that I showed you before, the time diagram, where we draw the Earth, we draw the South Pole, and then at the top of the circle, instead of putting Greenwich, I find it easier to put our position. So that's us. And then down here, technically this isn't us, this is our zenith, but the zenith and our position are the same. So down here is the nadir. Now we have the Earth centered around our position. The next thing we need to do is we need to actually graphically display what our position is. And that's based off of our longitude. So that's based off of our dead reckoning position of the time. You could see we used the 18 degrees 37 minutes north to find our assumed latitude. Now we're going to go over to our longitude of our DR position. We're got 108 degrees 20 minutes west. Now, that does not need to be precise. All that needs to show is, hey, if we're 108 degrees west, then where would Greenwich be on this chart? Well, that's 90 degrees, so Greenwich would be there, right? Just a little bit below 90. Doesn't even need to be perfect, it's just generally in this direction. You label that Greenwich. And then, for simplicity's sake, on this side, you draw a little g, which is the anti-meridian, the opposite side of the Earth from the prime meridian. So 180 degrees east or west. So here we have us, here we have Greenwich, and here's our position relative to Greenwich, which is equivalent to our longitude. So this is longitude right here, and it's 108 degrees 20 minutes west, based on our DR position. So not guaranteed to be true, but that's where we should be. Now we can put the sun. So our sun, we said, had a GHA of 83 degrees, 7.0 minutes. Remember, GHA only ever goes to the west. It is never going in another direction. It's only ever going to the west. So in that case, we can know that the GHA is going this way. So if we're 83 degrees away from the prime meridian in this direction, well, we're not exactly, this is more than 90, so I'd say 83 is that. And we label that as the sun. So here's the sun. And then this right here is GHA. So if this arc is our longitude and this arc is our GHA, our LHA, remember, is the westward angle from us to the sun. So if it's how far we are from here, it is kind of this distance, but we have to go from us to them going west. So it's actually this right here. That is our GHA. Now that is 360 minus this little bit right here. So we do need to find that little bit. And that little bit right there is equivalent to this minus this. So in other words, in this situation, LHA, and I recommend you write this out every time so you don't get yourself confused. Never just, like the acronym, the mnemonic is west add east or east add west subtract. East add west subtract. But I don't want you to memorize that. I want you to understand what's going on. So in this case, LHA, I should label that. LHA is equal to 360 for the full circle minus longitude minus GHA. So longitude minus GHA is this minus this, which gets us this. Then that we subtract from 360, and that gets us this. So that's how we find our true LHA. So now that we have this, we can just input our specific numbers. So 360 minus, what is our longitude? Well, that's where we stop. Because the one thing we want to make sure when we do this is we want our LHA to come out to be a true number or a whole number. It doesn't need to be exact because we're using a DR position anyway. So it doesn't really matter whether we're like 2 or 3 miles to one side or the other because we already approximated our location. What we do want to do though, because if you remember in Pub 229, every page is based off of a single LHA in whole numbers, is we want this to be worth whole number values. Now, the only way to do that is we manipulate our minute values of our assumed longitude to be the necessary values so that when we apply it to our GHA, we get a whole number of degrees. And you can see in this situation, we're doing longitude minus GHA, so they're subtracting from one another. So you could just do whatever you need to do to get this to equal 0. In fact, we can already write down here that the LHA has a minute value of 0 minutes. So what do you need to subtract? What do you need to subtract 7 minutes from to get 0? You need to subtract 7. So we need our assumed longitude to have a minute value of 7 minutes. We also need our, and that is why, no, okay, whatever. We'll go on. We need 7 minutes. So we can right here, our longitude will be 07.0 minutes. We haven't decided our degrees yet. We also know our GHA is 0.83 degrees, 07.0 minutes. So now the only thing we need to find is the degree value of our longitude. Now, I know we said it doesn't matter, we don't need to be precisely at our longitude value, but we do want to be close. Because if we're not close, then things start to get wonky. So we want to get, the rule is within 30 minutes to either side of the exact DR longitude is close enough that that's satisfactory to us. So whatever value, whatever number we can find that has a minute value of 7 minutes and is within 30 minutes to either side of this longitude, that's fine. And the best way to do that is to come over here and you draw it out by drawing 3 meridians, having the central meridian be, well, what I've found is the best way to do it is you have this be the 3 different options available to you for what could be our assumed longitude. So we know they all have to be 7 minutes in for a minute value. So everything is 07.0, 07.0. 7.0, but they all have different degree values. And seeing as we're working with 108, let's set that as the central one and do 108 degrees. We're going west, 109 degrees and 107 degrees. And say, if these are all of our options for what we could have as our assumed longitude, because it needs to be, have this minute value and be in generally the same area, which one of them is closest to our DR position? Well, the way we do that is now we draw where our DR position would fall in this situation. So if we had 108 degrees, 20 minutes west, and these were our options, 108 degrees, 20 minutes would be somewhere probably over here. 108 degrees, 20 minutes. Closest to what we set our central meridian as. Now that won't always happen. You'd be surprised. Sometimes it lands like over here, and then we want to pick this one. But in this case, it landed closest to this one right here, meaning this is our closest assumed longitude to what our actual longitude should be. So this is what we should base it off of. So now we set our assumed longitude as 108 degrees, 7.0 minutes west. I know that was confusing. We're going to do it 2 more times so it clears things up. But now that we've got our assumed longitude and our GHA, and we know that our formula is going to be 360 minus assumed longitude minus GHA, we can carry over the degree values of 108 degrees. And now we can do this minus this. You get that answer. You subtract it from 360, and that will be our LHA. You also know that the 7 minutes cancel out because they're just going to be 7.0 minus 7.0, so you don't even need to bother calculating that. So you're really just doing 108 minus 83, get that answer, and then subtract it from 360. So 108 minus 83, we got 25, so you 360 minus 25, 335. Our LHA is 335 degrees. And now we have the third and final value we need to actually be able to go into the book and calculate our computed height. And it took me 12 minutes to do it. Okay, we're gonna go to the next one. Next problem. We're doing the same thing. We're trying to find our assumed longitude and our LHA. Now for this one, we're actually gonna start by calculating our assumed longitude because I think it's easier to do that first. Because we can say, knowing this process now, understanding it in advance, we can start to work on calculating it. So we know we're in the west. Remember, like I said before, east add, west subtract. So we know we're going to be subtracting the minute values just like we did before. And when you need to subtract them, the minute values need to be equal to one another. So if the minute values of the GHA are 16.1, then the minute values of the assumed longitude are also 16.1. That much we can figure out in advance. And if you don't believe me, draw this out to figure it out. We're going to do that in a second, but I just needed to get that out of the way first. So now that that's done, now we can start calculating the assumed longitude portion. So if our assumed longitude has to have a minute value of 16.1, then we can set up our 3 meridians, and they all can have a minute value of 16.1. And by the way, you don't need to graphically draw this out, but I find it easier. I think it's helpful to draw it out graphically. Now we need to add in the degree values. Now, the degree of our DR position is 121 degrees, 56 minutes west. So we're going to set 121 as our central. So 121 degrees. Then this would be, we're in the west, so this would be 120 degrees. And this would be 122 degrees. So if our DR longitude is 121.56, which of these 3 would it be closest to? Would it be closest to this, or this, or this? it would actually be closest to this one. You know, right here is 121 degrees 56 minutes west. Doesn't matter that it's the same degree value as this one over here. You can see it's only 20 minutes away from this point, whereas it's 30 minutes or 40 minutes away from this one. So it's closest to this degree value right here, meaning we should use this degree value as our assumed longitude. So our assumed longitude is 122 degrees 16.1 minutes. Now, I already said we know that we need to subtract these two, but I want to do the diagram again just so this gets stuck in your head. So now that we have our assumed longitude, we can draw a circle, set the South Pole. At the top of the circle is our position. At the bottom is our nadir. Now we set our longitude, meaning we need to locate Greenwich. So if our longitude was just about 121 degrees west, and that means that Greenwich is significantly more than 90 degrees to our right here. It's probably down like this. So here's Greenwich. Here's the anti-meridian. So that right there is our longitude. Technically our assumed longitude, to be more accurate. And it is our distance away from Greenwich. Now we want to place the sun. The sun has a GHA of 79 degrees, 16.1 minutes. So where would that fall? Well, that would fall right somewhere around there. There's the sun. And here is the sun's GHA. GHA. Our LHA is from us all the way around to the sun. I just realized, wait, did I? Yeah, that's fine. Okay, so then to find this, we need to do 360 minus this value. So LHA, once again, is equal to 360 minus longitude, assumed longitude, minus GHA. So we're going to do assumed longitude minus GHA, and then we're going to do 360 minus that. So the minutes cancel out, and we're just doing 122 minus 79. 122 minus 79. Then we do 360 minus answer. So the answer is 43, so we do subtract from 43, and we get 317 degrees. Remember, this is technically 0.0 minutes, but we don't even need to write that. It doesn't matter. We know that everything we do always comes out to be exactly an exact degree value, so 317 degrees of LHA. Now, these two problems are pretty similar to each other, so let's do the last one to show something slightly different. This isn't every single possible situation where because we could also be in the east, the sun could be in the east, the sun could be in the west, and we could be in the east. Different things could happen. So this is our third example. Not indicative of everything, but if ever you're not sure how to do this math, what your equation should be, draw it out and it will make it a lot clearer. So here, we need to find assumed longitude. We need to find LHA. The difference is, this one is in the east. So let's actually draw the diagram out first, and then we'll start dealing with the assumed longitude down here. So we draw our diagram, draw the South Pole. Here's us. Here's the nadir. But where is Greenwich now? Greenwich is not over here. We're in the east. We're east of Greenwich. 78 degrees east. So Greenwich is actually over here. And now you can imagine if this is the prime meridian, 78 degrees east would be around here. Then we draw the anti-meridian. Good. And now we can draw the sun. The sun is, what did we say? The GHA is 232 degrees. So the GHA is more than 180. Remember, it's always going from Greenwich around to the sun. So 232 degrees from here gets around there. I don't know exactly. I just drew something. It's approximately that way. Meaning, here is our longitude, our assumed longitude technically. Here is our GHA. Our LHA is that. Meaning in this situation, where we are in the east, it doesn't even matter whether the sun is in the east or in the west. If it was in the west, this would all still be true. But if we're in the east, then LHA is equal to assumed longitude plus GHA. There's no 360 plus or minus. It's just you add this and you add this and you get the full LHA. So that means that we need to add the minute values together instead of subtracting the minute values together. So instead of just setting them equal to one another, we can't do that because then if we set them equal to one another, they wouldn't add to 360. Or they wouldn't add to 60, I'm sorry. We have to set the assumed longitude minutes to some value that once added to 33.7 is equivalent to 60. Meaning we have to set the complement. And all you need to do there is you just do 60 minus whatever these are. 33.7. So you do 60 minus the minute value of the GHA. So here we go, 60 minus 33.7 gets us 26.3. 26.3 minutes. Because when these two are added together, they come out to a 0 because they come out to 60. They create a whole, 60, 0, because they create a whole degree value. Makes everything a lot easier to work with. You don't have to do just as much work. And you get a whole degree of LHA. You also have to remember that you're going to carry the 1 here as a result. Now we know that this is the minute value we need for our assumed longitude. So we set our 3 lines. They all have a minute value of 26.3. Wait, is that within view? It's barely within view. 26.3 minutes, sorry. And then over here, 26.3 minutes. Now, working with generally 78 degrees east, so we're going to set the middle of these 3 options as 078 degrees. And then because we're going east, this is 079 degrees. And this is 077 degrees. And now we have to say, if these are our 3 options for assumed longitudes, where does 78 degrees, 29 minutes fall? It doesn't fall very close to 77 degrees 26 or to 79 degrees 26. So in this case, it would fall right around there, maybe even a lot closer, maybe like there, as 078 degrees 29 minutes east, right there. Meaning this is our closest meridian that has the correct minute value that we're looking for. So this is the one we use as our assumed longitude. 078 degrees, 26.3 minutes. Now that we have our exact assumed longitude and we have our formula, we know that we're going to add our assumed longitude to our GHA. We can finally find LHA. So we do, first we add the minutes. We already know that these 2 add to 60, and therefore they become 0, and therefore they carry a 1. So now we have 232 plus 1 is 233 plus 78. So we do 233 plus 78, 311. Our LHA is 311 degrees. So no matter what your problem is, what you need to do, first of all, is you need to pick if you're in the east or the west based off of your DR position. From there, you very quickly can figure out whether you're going to be adding or subtracting your minute values of your assumed longitude. If you're in the east, you're going to add them like we did here, here. You're going to add them, meaning you have to set your minute value to be 60 minus whatever your GHA minute value is. If you're in the west, you're going to subtract them, meaning you just set them equal to the minute value of your GHA. Nice and simple. And then once you've found that, you can set 3 lines, each of which have the minute value that you've already selected as being the minute value that you're going to work with. And then your degree values are all 3 options that are the closest to the DR position you chose. So if it's 78, you got 78, you got 79, you got 77. If it's 108, you got 108, 109, 107, and so on. And then once you've set these 3 meridians, you can very quickly choose which of these is closest to my degree, to my DR position that I've already selected for this problem. And whichever one is closest, you pick that as your assumed longitude. It doesn't need to be the one in the center. It could be on either of the side. You pick it as your assumed longitude, you write it out, and now you do the math. Following the formula you've already created, whether it's subtracting or adding, you follow that formula with the GHA and the assumed longitude, and you get your LHA, which is the third of the 3 problems that you're going to need to calculate your sextant height. Now remember, it's not always going to be you're here, Greenwich is here, the sun is here, in which case this is GHA and this is longitude. Sometimes it'll be you're here and Greenwich is here and the sun is here, and so this is LHA and this is longitude. And then sometimes it might be you're here, here, and Greenwich is here, and the sun is here, and so this is longitude, and this is LHA, and this is GHA, and so on. So these diagrams are going to change. They're not always going to be exactly the same as the 3 that I drew out here, which is why, even though the formula will only ever come out to be plus east subtract west, I do encourage you to draw it out every single time so you don't confuse yourself. It will guarantee that you make sure you have the right formula to actually find the correct LHA so you can move on from there. Trust me, the work is worth it. It'll get you the correct answer.